You're on again. It's following you again.
Thank you. So the wave particle duality theory, I guess, is kind of the idea that light behaves as both a wave and a particle. And this kind of came about because there are a lot of experiments with light, and in order to support different experiments, sometimes the scientists would say, like, oh, it acts like a wave, and then other types would be like, no, it definitely acts like a particle. So it's kind of going with that, where different experiments kind of prove different things and need it to be different things. And so it's both. There's a career day, can't decide what to be. But so that's
That's just your
yeah, sorry, Schrodinger's cat thing, yeah. But this is kind of a big thing in modern physics and newer things from the late last century. So it acts like a wave, and you can see this in multiple ways where you know that waves diffract and they show interference, and light also does that. And so that's kind of proof that it must act like a wave. So you can also have with water, light also behaves that way. Also, as we just discussed, light can be polarized, which is a wave thing. And I believe you guys talked about the Doppler effect, where you know it's the NASCAR sound. And so you can see that in light when you look at like the stars, and they talk about like the redshift in starlight when they're moving away. So that's more evidence that light acts like waves. That can be polarized, it's got the Doppler effect. But it also acts like a particle, which is where things start getting confusing. Because it has momentum, which is from a guy named Compton. He wasn't straight out of, but he was just, that was his name. And so he had an experiment where he shot a photon and it hit an electron, and the electron scattered, but so did the photon, which proves that light must have momentum because it just knocked an electron away. Even though photons don't have mass, it just seems contrary. And then, kind of before that came the idea that light comes in discrete amounts called photons, so light is quantized in little packets called photon, which is massless but has enough energy that it can knock away an electron. And then the photoelectric effect was one of Einstein's theories that was supported by the Compton effect. And so that's the idea where you have a sheet of metal. That's the base. And you have a light wave come in, and it knocks off an electron. And so that's what the photoelectric effect is. So light, which seemingly has no mass, has enough momentum that it can knock off an electron, which seems hard to believe. But so that's what Einstein proved, and Compton's theory helped support that. And so that's how solar panels work, which is kind of cool, amazing. And then de Broglie also helped with the idea by saying that particles can have wave properties like momentum and interference. But at the same time, he also says that like every object has kind of wave-like behavior, where like in physics, oftentimes we'll talk about how you can find the wavelength of a baseball. And so every object has a wavelength. It's just the more massive it is, and like the slower it's going, I guess, the bigger the wavelength. So like a baseball would have a huge wavelength, while a photon would have a very small, short wavelength. So that's more support for wave having a particle nature to it. So then I just kind of summarized it on this page, where waves have diffraction, interference, reflection, or refraction, which light also does. None can be polarized and has the Doppler effect. And then particles they're quantized into little packets and has momentum, which is thanks to Compton, de Broglie, and Einstein, which is all, I had a whole class about that, which is kind of cool. Modern physics. So that's all I've got for you on wave-particle duality. And then there's a short video, I think it's like 6 minutes, about the double slit experiment, and kind of what that helped entail for modern physics. Yeah.
That's good. Just real quickly, so most of you were in Mr. Segal's, a lot of you were in Mr. Segal's class. He shows the Dr. Quantum video, and it talks about that. This is the same idea. You've been exposed to that before, the whole idea of that. And so this is another physicist explaining it a different way.
Yeah, do you guys have any questions on like photoelectric effects or anything that side of polarization? Yeah?
The photoelectric effect, that like when the metal glows?
I think so. Yeah. Well, that's like, yeah, like in the solar panels, that's like how they create the electricity from it. And so like the light hits it and then knocks off electrons, which then creates the current in the circuit or how they're collecting it. Yeah.
So I'm kind of confused. Like, how does if something has no net? No, it's not like how. Just like how it could like bump an electron. Like, how does that work?
Okay. I gave myself notes in case things came up. Okay. So there's an equation that is momentum is Planck's constant over the wavelength, which comes from the fact the energy of a photon is P times C, which is the momentum times speed of light, I think? Yeah. So I think it's kind of comes down to when you're working with things at the speed of light, there's kind of like exceptions to regular laws of momentum. And so, yeah, it has momentum because you just kind of, it has a wavelength, and then Planck's constant is kind of just a thing. It's one of those numbers that like you find out in chemistry and physics, and then you use it like every day for the rest of your life, which is sad. But yeah, so it comes from the fact that this is the energy of the photon, and then because there's the equation E equals hc over lambda. So the energy of a photon comes from the Planck's constant times the speed of light over the wavelength, and that becomes since E equals PC, you get PC equals hc over lambda, and the c's cancel, so you get momentum equals hr. So it comes from the fact that the energy of a photon is its momentum times the speed of light, which then the speed of light cancels out, so you get the momentum is h over lambda. So it has momentum despite not having mass, which is really weird, but
Did that help you a little bit?
yeah.
So does that mean that the light slows down a little bit because it hits like a little light ball is like smashing into an electron ball, and then
Actually, that's kind of exactly how in this video. They have little light balls, so you're laughing, but that's how they.
well, does it slow down at all after hitting it?
Well, like the Compton effect was where you had your photon, and then it was going, and it hits an electron,
Yeah.
and then the electron scattered, and the photon also scattered. And so, since photons move at the speed of light, I think it's still moving at the speed of light.
It doesn't change. I'm going to help you here.
Yeah.
It doesn't change the velocity because they all move at the speed of light, but it goes to a lower energy light wave, kind of like if it was blue light and then it was then red light.
So it gets
And so
bigger
it still moves at the exact same speed, but the frequency will get bigger and or smaller, and the wavelength will
Yeah.
get bigger.
Makes sense.
So what happens is it does lose some energy, and it only happens with really high energy light waves.
Yeah, and there's.
So if you have an energetic enough photon, you can actually move like a subatomic particle with it, which is crazy because it doesn't have any mass, but they act like pool balls sitting together, just like conservation of momentum that we learned before.
So it's like elastic collision, right?
Yeah, it'd be an elastic collision.
Yeah.
And it follows conservation of momentum laws, which is crazy, which is kind of mind-numbing, but that's why it's high-end stuff.
Modern physics is where you start getting into all the relativity and stuff, so it hurts your brain. But it's cool. It's fun stuff. Maybe. Any other questions or else? Yeah?
Alright, I got another one. You know how you were saying like a photon has a wavelength and a baseball has a wavelength?
Yeah.
So it's like that wavelength, when you throw a baseball, does it like follow the baseball or like how is it produced?
Yeah, I guess. Like you have a wavelength like when you're walking, it's just a really huge wavelength.
Oh, okay.
so it's just like not noticeable.
No, that's it. No, sorry.
Yeah, so every object, every moving object has a wavelength, is what de Broglie's whole thing was, which is kind of a weird thing about, because you only think about like light, waves, and photons having wavelengths, but yeah, every object.
Where that's important is not so much about baseballs and walking, but like an electron microscope. And so what happens is that when you have electrons, when the particles get small enough, all right, when the particles get small enough, the wavelengths or the wavelengths also get small, and so the frequencies get high. That's the principle behind like electron microscopes. So that you're actually using particles, but you're using the wave-like properties to reflect off things and to see things that you couldn't normally see with visible light.
I don't know how people come up with these ideas, but they do.
I wonder how you count them, like, see that whole thing. You're a really good microscope.
I have no idea. I've learned about Compton scattering and the Compton effect, but I haven't actually nobody's ever actually really explained the whole experiment. How to discover that. So I should look that up. Good. Anything else? Sorry.
Let's watch some video and see if it answers.
It'll probably raise a lot more questions.
It might. It might.
Like, it's so confusing.
Weird sound.
All right, I'm gonna